Hello, my name is Steve Goldberg, publisher for Audio Magazine. As you know, Audio has been offering our readers for over 60 years the most discriminating editorial on the best and most prolific audio equipment. Now we're trying to take it one step further and offer you the most important information on the world of digital audio. Audio and Magazine has joined with Sony to present Len Feldman from Audio Magazine. Len is our senior technical editor and has been in the industry for over 25 years. And what Len Feldman will be talking to you today about is all the new innovations in the world of digital audio. It is encompassing, however, it is very interesting, and I feel you'll totally enjoy this. Thank you very much.
To start things off, there might be one or two of you out there who do not quite understand the distinction between analog recording or analog audio and digital. So in about 35 seconds or 40 seconds, I'm going to take you through a mental transition from the world of analog audio to digital, and then we'll get to the heart of the matter. To begin with, we represent audio, or an audio waveform, in sort of this way, representing an amplitude and a complex pattern of sound waves. As I speak to you, if a microphone were picking it up, we might amplify it with an amplifier, apply the results to a cutting head on a disc cutter, and it would make wiggles in a groove corresponding to the sound waves that would look perhaps like that. Analogous, or analog, to what I am saying, in a continuous time domain. But there's another way of looking at this same pattern. We could look at it as a series of individual instantaneous amplitudes, or samples, if you will, and we could express those samples in a number. We could say that at this point it's worth, maybe 10 boxes, and at this point 8 boxes, and so on. But instead of using our familiar decimal system of notation, we choose to use a binary numbering system, which, as many of you probably know, is a numbering system that consists simply of zeros and ones. There, just as we can talk in base 10, we can also talk in base 2 numbering systems. And this is a convenience in computer language and in the world of digital audio. Now, each one of those instantaneous samples, if we take enough of them and if we express them accurately enough, can represent that analog waveform. And so in those few short slides, you've made the mental transition from analog to digital audio. But a few things you should know about this digital concept. The number of zeros and ones that we use to create these number values, these sample values, can be anything from just a few to a many. If we were to have a crude system in which each sample only used 8 0 and 1 combinations, the most numbers we could come up with in such a system would be only 256. Hardly enough to describe the infinite variations of an analog sound wave. If we move up to a 14-bit system, and there have been some 14-bit digital audio systems in the past, why, suddenly we have available over 16,000 possible levels or number values with which to take these samples and describe them. Finally, if we get to the 16-bit format, which in fact we do use in compact discs, we have an astounding number, over 65,000. In computer language, we'd call this a 64K capacity. And that's quite enough to accurately describe any complex musical waveform, providing we take enough samples per second. And in this particular format of the compact disc, we sample at a rate of 44,100 samples per second. We'll get to the reason for that shortly. Now, what about the quality of the system? If we were to use an 8-bit system such as I described, besides the fact that we couldn't accurately describe the waveform, and therefore we'd have distortion in effect, we also would be limited as to the amount of signal-to-noise ratio or dynamic range that we could encompass or contain in such a crude system. Now, dynamic range, simply defined, is the difference between the softest sound of the music and the loudest sound, as measured in decibels. In an 8-bit system, that would be limited to only 48 dB. You get about 6 dB per bit, if you want to think of it that way. Now, everybody knows that 48 dB is not very much high fidelity. We could do that well with a handheld cheap cassette deck using the cheapest tape around. We could get 48 dB of signal to noise or dynamic range. Again, if we move to 14 bits, Suddenly our capacity increases by that same formula to 84 dB. And finally, in a 16-bit system such as we use in compact disc, we have a 96 dB theoretical dynamic range, or signal-to-noise ratio. Now, the strange thing is that we don't need 96 dB to fully contain the dynamics of real music. In the live instance, a musical performance rarely exceeds maybe 70 dB maximum dynamic range, from loudest loud to softest soft. But that's where we run into the most wonderful part of this whole CD technology, because what the recording engineer will do will take that 70 dB of dynamic range and put it up at the top of that available 96 dB within the compact disc format. So now look what happens. You turn up your volume control until you hear the softest sounds of the music. That's what you want. That's your reference level. Well, at that point, the noise level, and make no mistake about it, there is noise on a compact disc, but at that point of adjustment, it's 20 to 25 dB below your threshold of audibility. So you never hear the noise on a compact disc. What we're going to spend the next few minutes on is basically talking about what has evolved from the first generation of compact disc players to the third or fourth generation that we enjoy today. The co-developer, not Sony, the other developer, Philips, who were joined with Sony in developing this format, ran an ad which I think was unfortunate. In this country, they're distributed as Magnavox, by the way. And Magnavox first players, they used to run this ad that said, "Perfect sound now and forever." And that was sad in a way because, first of all, in the high-fidelity fraternity, I think we never feel that we've reached perfect sound. We're ever closer to it. And indeed, those first compact disc players were a remarkable improvement and a remarkable achievement compared to what had come before. But compared to today's compact disc players, they were far from perfect. For that matter, I wouldn't say today's are perfect either, but they're a lot closer to perfection than that first generation. And one of the reasons why is illustrated by a part of this block diagram, which I've isolated here. You see that multiple clock thing, the yellow symbols there represent the timing devices needed to control that 44,100 sampling rate per second that I talked about. There has to be a clock mechanism very accurately controlled, very much like the quartz crystal that controls our wristwatches, that maintains that 44.1 thousand sampling rate perfectly. In the early players, they had not yet developed or spent the money to develop discrete or complete integrated chips or integrated circuits that would contain all the elements necessary to control that timing mechanism. So very often you had these multiple clock designs in which several different chips all had that 44.1 timing device in them. And unfortunately, they weren't always synchronized with respect to each other. And that could lead to problems, as you'll see in a moment. In the modern generation of players, they have developed single chips that do all the functions of those other ones and therefore require only a single master clock. And if you're wondering what that means to you audibly, which is the bottom line, let me show you something we did in the lab. Now, this is called a spectrum analysis. It's simply a sweeping of frequencies from 0 hertz all the way up past audibility to 100,000 hertz, or 100,000 cycles per second. All right? We play a test disc that contains only a single tone, which is represented by this tall spike at the output of the player. We connect the output of the player to this spectrum analyzer, as it's called, and we sweep frequencies from 0 to 100,000. The only thing that should have appeared at the output is this one tall spike that you see. That's the actual tone recorded on the test disc. But look at all the other things that came out with it. Things that weren't on the disc at all. These are spurious outputs that are generated partly by that multiple clock situation we talked about, and partly by incorrect filtration or incorrect filtering, which I'll get to in a couple of moments. Now, take that same compact disc, test disc, with that same tone, which I think was about 440 hertz or thereabouts, and play it on one of the modern master clock design, digital filtered players of today, and this is what you get. Now, I think you'll agree, even without actually hearing the comparison, that you'd hear a difference between the ones that we showed a moment ago and something that is only producing the pure tone that's actually recorded on the disc. By the way, if I can step back a moment, while this is the only product, spurious product, that actually falls within the audio range, these other ones that are truly outside audibility, they're above 20,000 hertz, which is the limits of human hearing. Nevertheless, they can beat or heterodyne or mix with the 44.1 kilohertz sampling rate. And when that happens, it throws down intermodulation distortion into the audible range. And remember, in some of the early players, people used to complain that they sounded grainy and gritty at the top and all of those adjectives that were used. Part of it was this very thing we're looking at. Not all of it, to be sure. A lot of it was in the software as well. Poor recordings or poor recording technique. But some of it was in this comparison study we've just shown. Okay, basically what we're talking about then are little incremental improvements that have come from generation to generation in these 3 years since the first introduction. Another new one that's showing up in a couple of manufacturers' players already is called optical transfer of the digital data. Now, you're all probably familiar with the term fiber optics as being used now in telephone communication, telecommunications of all sorts. It's been found that if you can interrupt the hard wiring path of the signal in the digital portion of a CD player, you will slightly further improve the sound quality, because that hard wiring can be influenced by such things as the power transformer with its magnetic field that's also got to be present inside the body of the CD player. And any hard wiring that you can eliminate by using optical coupling such as this is advantageous. Again, a small incremental improvement. We're not talking about big shades of sonic difference, but when you start adding all of these things together, they do matter in what you hear. So we'll see more of this in all probability as well. Now, I said before, I talked about both the filtering aspect and the multiple clock design versus the single clock. Let's spend a moment on this question of filtering. You know, you're faced with a dilemma in digital. First of all, if you agree that 20 to 20,000 is the amount of frequency response you want to be able to store in any digital medium, then it is also a rule that the sampling rate has to be at least twice as high as the highest frequency you want to record. I mean, that's fundamental to any digital sampling process. And so, in this case, if we want to be able to store music up to 20 kilohertz, our minimum sampling frequency would have been 40. It was standardized at 44.1 for various reasons. But notice this distribution of components. Here's the music. This is the only part we're interested in. But when you have a 44.1 kilohertz sampling rate out here, as we do, you develop what's listed here as modulation noise products, actually sidebands is what I call them, which extend plus or minus the same 20 kilohertz bandwidth as the music. Now that puts the lowest end of that modulation noise at about 24.1. Now look at the dilemma we have. In digital, we want to have perfectly flat response out to here, but then we must filter sharply and quickly so that none of this material gets into the output. Pretty difficult filtering problem. Flat out to 20 and almost infinite attenuation at 24.1. In the first generation of players, this was done with what they called brick wall or very steep multipole filters. All right? These were analog filters at the output, very sharp, very steep filtering. But there are two problems that arise with that. The first is, in a mass-produced item such as this, it's difficult, if not impossible, to have every filter circuit come out exactly alike and have the perfect cutoff point at 20 kilohertz. And so, in fact, many of the first players I used to measure, instead of really going out flat to 20, started to roll off at 17 or 18, and by 20, some of them were down as much as 3, 4 dB. Now, to me, that wasn't very serious, because I'm an older fella and I don't hear much past 16.5 anyway. But that was not the big problem. The big problem, the second problem inherent in these steep filters, is called phase shift or time delay. Now, it is a fact when you use this type of filter, as you get higher and higher in frequency, the high frequencies are displaced in time relative to the lower frequencies. Now, does that mean anything? Well, there's a lot of argument about that. But a musical instrument, when you play a piano, a 440 or A on a piano and A on a trumpet, they don't sound alike, even though both are playing middle A. The reason is that you have various amounts and time relationships of overtones or harmonics associated with each musical instrument that may extend way out to the limits of human hearing. And a lot of people feel that those harmonics or overtones should be kept in their correct time relationship to the fundamental. Well, filters such as this destroys that correct time relationship severely. Now again, I say, it can be argued, there are many people who say you can't hear the effects of phase shift. And indeed, in monophonic that may be true, in mono listening. But I have found several times that you get this severe phase shift in a stereo situation with two speakers, and instead of that stereo image being really fixed and having the depth that you expect from stereo, there is sort of a vagueness or a wandering. You lose that stereo imaging with extremes of phase shift such as this. And I think most everyone who has heard that comparison would agree that extreme phase shift tends to destroy the perfect stereo imaging. So, how do we get around it? Well, early on, even as early as the second generation of players, they discovered something called oversampling and digital filtering. And those two terms always go together, by the way. You'll see them in the advertising literature in certain CD players, always joined. What does that mean? Well, if we were to incorporate in our compact disc player a timing frequency, not of 44.1 like it is on the disc, but let's say double that frequency, or 88.2 kilohertz. Now, don't misunderstand. We're not saying we're creating a new standard for CDs. There's only one standard for CDs. The samples on the CD itself are at 44.1 thousand per second. What we're saying is, try to think of this as if the sampling frequency within the CD player is looking at each sample twice. That's a good way of looking at it. It's mathematically not totally valid, but it's an easy way to understand what's happening. In that case, with a new clock frequency of 88.2, that whole modulation noise problem that we talked about earlier is shifted up in frequency about a higher center. That being the case, the lowest frequency we need to be concerned about now is at 68.2, or far enough away from the music so that with the aid of a very gentle sloping filter, which begins to cut way outside the passband of interest, we can accomplish sufficient filtering so that none of this gets back into here. And of course, we eliminate the phase shift problem that we talked about. So to summarize that, the old way, the new way, with oversampling and digital filtering. Now, on this digital filtering issue, that's kind of interesting because just about everybody today is advertising their machines as having digital filtering. But not all digital filters are alike. As it happens, we measured 3 of them recently. One of them claimed digital filtering, and indeed it did have digital filtering, but the amount of attenuation outside the passband was only 40 dB, clearly not enough to do the job we're talking about. A second one was at 55 dB, and of course 80 dB. I might mention that if you were to try to do this in an analog multipole filter, to get this same steep attenuation right outside the passband, it would take a 96-pole filter. For those of you who know what that means, 96 sequential circuits, in effect, to accomplish that degree of attenuation, which is unrealizable in the real world of analog filters. But this is what we can do with digital filters. Here we have another subject that seems to be popping up more and more, and that has to do with the laser pickup itself. A lot of people now are stressing the fact that their equipment incorporates a 3-beam laser pickup. Now, first let me clarify that no CD player has 3 laser pickups in it. It's one laser semiconductor, but optically, using lenses and prisms, they split the beam, the light beam from the laser, into 3 separate beams. And the reason for that is fairly obvious, I think, because after all, nothing is touching a CD when it plays. There's no grooves, there's no needle or anything like that. It's just a beam of light. So in addition to tracking the audio information, there has to be some means to tell that laser pickup that's hovering below the surface of the disc where to go. One of the functions of this 3-beam approach is just that. That center spot, and those blue lines, of course, are the little pits that are being read by the laser beam. The center spot tracks the audio information itself, whereas the 2 side spots actually keep that laser pickup on track, or guiding it across the spirals of the CD. Now, I said that more and more manufacturers seem to be going to this, and the reason probably is because it's a more effective means of tracking. You can do it with a single spot laser too. There are ways of doing it, and some of the earlier generation machines used a single spot laser. Changing it from a circle to an ellipse. There were many ways where a servo mechanism could sense that it was going off track and pull it back onto track. But because so many people have found this to be more effective, you'll find that many of the later generation players are employing this three-beam approach. It seems to do a little better job. Okay, this little picture isn't going to teach you much and really isn't going to tell you much, except I did want to include it for one reason. When I bought my first CD player about 3 years ago now, it was a CDP 101, the first model available. I got out there about 5 minutes after it became available and picked it up. And of course, being curious and of a lab mentality, I had to open it up. So I took the cover off, thereby voiding the warranty, I might add, and looked inside. And of course, it was just layer upon layer of circuit board. It was just so dense you couldn't stuff another resistor in there. From that early beginning, in 3 short years, we have come to this. This board measures 4 by 5 inches and contains all the circuitry needed in all this digital translation and all the other clever things that the modern player does on just a 4 by 5 circuit board. So I think we've come a long way, as I said. Whether you know it or not, compact discs are not stereo at all. We'd have to call them sequential mono. In that I mean there's only one bit stream coming out of there, that pickup. In other words, the zeros and ones are serial. They come out serially, one after the other. So what you have to do is, in the coding system on the disk, you have a few microseconds of left channel, followed by a few microseconds of right channel. And at the output, of course, this is all switched back and forth real fast, so that ultimately you get separate left and right information. But early on, using a single digital to analog converter, some mathematical genius figured out that by doing this, you encounter an 11.3 microsecond delay between the left and the right channel. Now, 11.3 microseconds, they said, that's got to be pretty serious. Well, later on, somebody else figured out, I want you to watch me closely now, that if you were to turn your head this much, that would be 11.3 microseconds displacement of your left and right ears, you see. Very serious indeed. But since we're all purists in the audio industry, you will now find that there are some players that indeed employ separate D to A converters for the left and right channel. And by properly delaying the left channel in advance, you know, by a circuit time delay, everything comes out exactly in time relationship as the 2 microphones, or however many microphones, picked up the left and right channel information in the original performance. I think the real reason we're seeing more dual D to A converters in CD players today is because the price of a D to A converter has come down tremendously, and it's not just such a big deal anymore to put in 2 of them instead of 1. Sonically, I frankly don't think it does all that much. And there are plenty of good CD players out there that still employ a single D to A converter. Here is a more serious innovation that has appeared recently, and this is an important one. In this CD format, there are some pretty sophisticated levels of error correction capability. For example, if there's a slight scratch and the laser cannot read a few samples, let's say, there's enough redundant information in the disc itself, built into the recording format, so that it'll pick up that information elsewhere and fill it in where it couldn't read it the first time. Okay, if there is, however, a deeper scratch or a bigger obscuration or opaque area on the surface of the disc, for whatever reason, dirt, dust, a scratch, the next thing it will do is what we call interpolation. Now, because it remembers what the last few samples were, and because the waveform is not going to change instantaneously, or very much instantaneously, the system sort of predicts what the next few samples would have been that it can't read, and it fills them in. So you don't hear anything wrong. You might get some distortion that way because it could be wrong during that time, but at least you won't get an interruption of the music. The third level is, if indeed it's so bad because, say, your kid has spread peanut butter on the disc or something like that, they just can't read a whole batch of information, then it mutes. Okay? It actually, you have a momentary interruption of the music, and perhaps some of you have heard that on some CDs. Or in some cases, it even seems to be like the proverbial broken record. It plays the same spiral over and over again. We've heard some of that, too, on defective discs. Okay. What developed here is an improved version of error detection, correction, interpolation, and muting. In this sense, if you get one of those severe dropouts where there's a lot of missing information, the system will still mute, But because it is able to detect the missing information more quickly than previous systems, it then puts a hold circuit on, or locks that pickup in place, so to speak, guiding it at the same rate that it would have been guided had there been information available, tracking information. Now, the beauty of this is that I don't know if this has happened to you, but sometimes if your player is not on a perfectly level surface, and if you get one of these serious mute situations, you may have been playing track 2 when it went into mute, and all of a sudden when it starts playing again, you're on track 7 because that poor laser pickup really was wandering. It didn't know where to go. It just slid across, and wherever it saw data, it started to read. In this case, that would not happen because it would lock that in place. And when data becomes available again, you would hear it perhaps having missed a few milliseconds or so of music, but it wouldn't be all over the place wandering. They demonstrated this new circuit in a very startling and effective demonstration. What they had was a disc, a CD, an ordinary CD, on which they had pasted a piece of black tape, which was 2 millimeters wide. Now that's 2,000 microns if you want to talk in millionths of a meter. And by reference, some of you who may read my reviews in audio know that I have a special defects disc that I use, and that has a wedge that goes out to 900 microns at the worst. That's 0.9 of 1 millimeter. And a lot of players today can get through that 900, but just barely. I mean, much beyond that they would miss track. Here was a disc that they had doctored up with this 2 millimeter wide electrical tape, that's all it was, pasted right across a radius, and they had one of these players equipped with this new circuit but with an external switch so that they could switch this new refinement on and off. And they put this disc in, and believe me, the player, without the thing turned on, without that circuit turned on, just spit the disc out again. It wouldn't even begin to read it, and that's happened on some discs too. It won't accept the disc. When they switched the switch on that introduced this circuit, not only did it accept the disc, it didn't even mute. It played as if there were no interruption in that music at all, which I regard as kind of miraculous because that is a greater missing error length than I had ever seen compensated for on any system. On the purely physical side, look what's happened, for example, to the laser pickup assembly itself. That old CDP 101 that I bought so soon had this monstrous thing for its laser pickup assembly. And of course, being as massive as it had to be driven by a worm gear driven motor. That was a pretty heavy, massive assembly. Look at contrast that with what we have today in the modern players. That's the same function as that. There's your laser pickup assembly, and it is 1/3 the mass of the earlier one, and 1/3 the size, roughly. Now, you might say, well, that's great for miniaturization, and that's what made possible the portable CD players, and all of that is true, but I think it goes deeper than that, because when you get down to this lower mass, a lighter weight pickup, it's also easier to move that thing quickly and accurately and maintain proper tracking. Again, this contributes to the more accurate, stable, reliable tracking of the player. In addition, that particular lightweight also enabled the use of a transport such as this, which I'll pass around amongst you, and this uses what's called a linear motor. There are no rotating parts on this at all. There's the laser pickup. It moves back and forth, and this magnetic coil up here is the motor. This is analogous to those popular science articles that always talk about the railroads we're going to have someday that will just move on a magnetic motor track, you know, with no rotating parts. Here it is. There's your railroad. You might want to look at that and pass it around if you would, and see the ease with which that entire assembly can move back and forth quickly. Now, in addition, that particular unit is actually a generation ahead of what was there a year ago. They started to use these linear motors about a year ago, but they mounted them on all metal chassis. And the very speed with which that assembly moved back and forth actually created resonances in the metal chassis. And again, you ran into some of this interpolation we were talking about because of poor tracking and vibration caused by the actual motion of the pickup itself. So, wouldn't you know, in the current generation, they've come up with a new material, an inert material consisting of a ceramic resin compound. And where you see these yellow shaded areas, they have sort of added that material to the unit you're passing around, and that damps out the resonances that were a problem in these fast-moving laser pickup assemblies. Now, to show you that this really does something, and it's not just gilding the lily, here is a graph taken of the conventional metal chassis version of that pickup assembly chassis, in which they purposely induced a resonance into the entire chassis, and it was of this amplitude, and it decayed, it damped out at this rate. As opposed to the new material, as you see, in the first place, the resonance never reached the amplitude of the all-metal chassis, and it also decayed or damped out much more quickly. Again, a minor improvement to be sure, but again, if you add all these little things together, they make for a better player. Well, what we've brought you to up to now is sort of the progress that's been made in these first 3 years, where we are today. And now the next thing we want to do is look ahead a little bit. And there you see what's coming very soon, one of the applications for that subcode output. Of course, you're going to have to buy another one of those famous black boxes, the peripherals as we call them, that will attach to the back of your CD player if it has this kind of subcode output availability, and that in turn will interface with a TV screen or a monitor or a TV set. And obviously, as you can see from the slide, there are many, many applications that could be applied to this. You see, on a compact disc, there's a capacity of, I think, roughly 13 billion pits. 13 billion on one compact disc. And we're only using about 5 billion of them for audio. So there's a lot of room left over. And one of the things that was set aside, and that they knew would be happening, would be digitally created graphics, still pictures. Not video, this is not movies, this is not a video real-life movies, this is digitally generated scenes or text on screen that would be available alongside the music. You see some suggestions there. One suggestion that we heard recently in Japan was the idea of perhaps selling a given musical disc for the car CD players, which of course exist now, and putting a road map on the disc as well. So sort of a musical triptych, if you will, like AAA used to do, and you have a little video screen in your dashboard, and as you ride along, you punch the button and get the next sequence of roads. I don't know how the police would cotton to a video screen in the front seat, but it's an idea. Anybody own a computer? Yeah. How much capacity on your discs? 360K or 390K? Yeah, floppies, in other words. Dual-sided, double density, yeah. 390K thereabouts. If you own a hard disk, if you were rich enough to have a hard disk computer, might have 10 megabytes or 20, right? 40. Well, look at that. That's what you can get on one CD if you use it for digital data, for computer data. Forget the audio now, okay? And in fact, we're already beginning to have some CDs issued for this purpose. For example, Grolier's Encyclopedia has issued their entire text of their entire encyclopedia on one CD, and it occupies only about 20% of the disc. Now, unhappily, they didn't put any pictures in with it. It's only text. They could have had room for a lot of pictures, and they may do that in the future when they update it. Now, you can buy that encyclopedia on disc form for $1,400. So you do need, of course, a special ROM. It's called CD-ROM, for read-only memory, because this is not a read-write situation like your floppies. You only have to have a database on it, and it stays fixed. You can't erase it or rewrite to it or anything like that. But for large databases, like an encyclopedia or a library or whatever, it's tremendous. More capacity than any magnetic medium could support. And again, this is in the same CD format that's developed for audio and for these digital graphics we were talking about. Now, I want to take it a step further, though. Now, look, we've talked about audio on CDs, and we've talked about pictures, or still pictures at least, and we've talked now about digital or computer data. The latest wrinkle that's going to come is what they call compact disc interactive, or CDI, where we combine all three of these visual and audible media in one format. And if you think about it, that could be the most wonderful educational tool or training tool in the future as a learning thing, by combining all these aspects, the digital data, the text, the audio, and the pictures. And that's going to happen, and to prove it, there are already committees working on creating the proper specifications and codes for this interactive form of CD. And that'll be with us very soon indeed. There's a familiar item, the D7. And what makes that possible, of course, is what I talked about earlier, the integration of all these multiple functions into a single chip. And what you see there is an 80-pin chip that's no bigger than my thumbnail that performs what 9 separate chips had to do in the earlier generations of CD players. It's all in one. And the other thing that's made possible by this kind of dedicated IC technology, or integrated circuit technology, is this. As you all know by now, there are CD players for cars. Have been for almost 2 years. And if I can just digress for a moment, I remember some 3 years ago, we were taken to Philips, actually 3.5 years ago, when they were first introducing the idea of CD. Several of us press people were invited to go to Holland, to Philips headquarters in Eindhoven, and they're the co-developers, as I mentioned. And they gave us a lot of tutorials and lectures about this coming technology of CD. And one engineer got up, I remember, on the last day, and he said, "And you know, gentlemen, someday we will have CD players even in cars." And we all kind of snickered, you know, and laughed. I said, "Maybe in Holland you will, but in New York, on the roads we have, forget it. Potholes and all that." So anyway, I was wrong and he was right. And when I got this first compact disc player for a car about 1.5 years ago, I was very excited and I wanted to get right to testing it. And I'm pretty sharp about these things. I knew not to connect it to 120 volts. I had a 12-volt power supply and all already. I'm really with it. And I hooked it up. And of course, it did great. I mean, the distortion was low and the frequency response was superb and no wow and flutter and all the nice things that you expect from a CD player. And when I got all done taking the numbers, I kind of paused and I said to myself, well, so what? This really doesn't prove a thing. How will it do on the road? Well, I had just bought a new '85 Oldsmobile, and I wasn't about to, you know, get into the dashboard and mess around. And I thought and thought, and I finally remembered that our technical editor, Ivan Berger, maybe your name is familiar to some of you, you read his stuff too. Ivan Berger, I knew, owns what I can best describe as a vintage Saab. This is an old car, okay? About a '68, I think. And I knew that it had seen better days, and it seemed to me that would be an ideal vehicle in which to try out this new car CD player. So I called up Ivan, and he being a purist, "Sure, I'll be right out, Len." And he came out to my lab, and we dutifully took out whatever he had in there and mounted this very player in the dashboard, and off we went. Well, I mean, we cruised the Long Island Expressway, which, although it's considered to be the world's longest parking lot, is also fairly smooth. So it didn't prove much there either, and I was getting kind of tired and didn't want to go into the city. And I finally had my final brainstorm, and that was to go in back of the supermarket where we shop, where in the parking lot they have these speed bumps, you know? You're supposed to go over them like 5 miles per hour. Well, I told you, Ivan is a purist, and no kidding, he went tearing over those things at 30 miles an hour, and you know what that feels like. I mean, but that thing tracked. It did not miss track, which to me was just incredible when you stop to think that we're dealing with pits that are 1.6 microns wide with a physical device hovering underneath trying to track these things while we're going bumpity-bump over these ruts in the road. Now, this slide, it's not too clear here, but it illustrates a new suspension system called a triple suspension system that totally isolates the moving parts, the moving mechanism of this new car CD mechanism from the outside world, from any shock or vibration or really hard knocks. It just won't miss track. And where that's being used is in a new product, which some of you may have seen. It's a 2-part unit. The only part that has to go up front in the driver's compartment is this little remote commander. And this unit, which contains the entire mechanism and also handles 10 discs. This is not just a car player, it's a car changer. This is in a hermetically sealed box which goes in the trunk of the car. Here's something you will never see in this country in this form. This, believe it or not, is a 120 disc CD changer. And the only place you'll find it is in Japan, and that requires a little bit of explanation. As many of you know, Japanese executives and business corporate people work very hard. They're dedicated. I mean, they put in long days, and they work hard and into the night. And when they finally wrap it up for the day, they like to relax, same as we do. Only they have rather different ways of relaxing. Cultural differences, you might say. And one of the things they will do is go to a place called a karaoke bar. Now, a karaoke bar is unique to Japan, and what it is a bar which might have one of these multiple CD players loaded up with 120 discs or so, but they won't be the discs you can buy here. They're specially made discs that are sort of at a part. They have the music without the vocal part, without the singer's part, the lyrics. And after a few sakes or Kirin beers, some of these fellas will have the energy and vitality to get up, and they have beautiful PA systems in these bars with lots of reverb so everybody sounds great on the microphone. And they sort of run it as a contest, as a sing-along contest. Who can out-sing the other guys? And they print the lyrics on sheets or they'll project them on slides. And usually they do Western songs, that is English songs, the popular songs of the day. And they love it. It's a very big fad in Japan. Now, a couple of years ago, I was in Japan, and when this craze was reaching its height, one of the gentlemen in engineering, or I guess it was in sales, asked me, Len-san, do you think we should export karaoke to the U.S.? You think it will sell there? And I said, Tago-san, I don't think it's our kind of thing. I mean, it's just not the sort of thing we would go for in this country. And, of course, it hasn't come. I think they realize that this is just a Japanese fun thing that might not go over here. However, I will tell you that 6 months ago, I was there again. I'm there about twice a year. And another host dragged me into one of these places for an evening, and wouldn't you know, within 10 minutes they had me up there singing as well. I mean, it is a lot of fun. But I show it for a reason, not to tell you a whole story about Japanese culture, but rather to tell you that just a few weeks ago, Sony did sign a deal with Seeburg. Remember Seeburg, makers of jukeboxes? And so we're going to see CDs in jukeboxes in the very near future. And that is a reality, and that will happen. If indeed we went from analog or LP records to digital records, then it is only logical perhaps that we should be going from analog tape recording, cassette tapes, open reel tape recorders and so on, to some form of digital audio tape recording. And of course we've already developed, we're very good at acronyms. We get the acronyms, DAT, long before we get the product. DAT, digital audio tape recorders. Well, the strange thing is, as early as 1977, if you wanted to, you could have done digital audio tape recording at home. Because it was in that year that Sony introduced the first of many digital audio processors, the PCM-1. Now, that baby weighed about 45 pounds, as I recall, and sold for about $5,500. But it was capable of taking two analog inputs, whether from microphone or line inputs, and converting them to a fixed, standardized digital code. And the only other thing you needed to maintain or to preserve that code on tape was something that could handle the high frequencies involved here. These pulses go up into the megahertz in frequency. And the only thing available in '77 that could do that was, you guessed it, a video recorder, a home VCR, which had been around for 2 years by that time. So, by combining such a device with a video recorder, which you then used only as a tape storage device, as a medium that could handle these high frequencies, you could have put together, in 1977, a home recording digital audio system that would beat what most professional recording studios had at the time. Now, over the years, such companies as Sansui and Technics and Sony have produced other PCM processors, lower in weight and lower in cost. So for about under $1,000, you could have a truly magnificent digital audio tape recording system. Okay, but when I speak about DAT now, that's not what I mean. In other words, this was sort of an offshoot or an afterthought that related to video. In effect, what you were doing with this combination, and you had to use two pieces of equipment, again, a video recorder plus a PCM processor, what you were doing was sort of fitting the digital information where the picture would normally go, like between the horizontal pulses, between the lines of the video picture. Instead of video scene, you were putting the little zeros and ones, the pulses or absence of pulses of this digital code. So it was kind of a makeshift arrangement. But as I say, that's not what we're after. We're after a dedicated system exclusively designed with audio in mind and optimized for digital audio recording. And after many years of deliberation, that is a reality today. Now, the reason this can work, either in video or in the format we're going to talk about, is because you see, in a video recorder, which this is a beta cassette, an inside view, while the tape itself only moves along horizontally at about 1 inch per second, the head drum that contains the record playhead is spinning around at 1800 RPM. So the relative tape to head speed, or writing speed as it's called, is not 1 inch per second, but more like 30 feet per second. That's why it can handle or contain these high frequencies necessary either for video or, in this case, for digital data storage. Well, the same sort of thing is going to be applied to this new system called RDAT, for Rotary Digital Audio Tape Recording. Before we look at that, however, a few size comparisons. Back there you see the VHS video cassette size, just for reference, and just in front of it, of course, is the beta cassette, which was always a little bit smaller, and finally the new 8mm video cassette, which is smaller still. These are 3 video recording cassettes. Another size comparison here. This is our good old friend, the 20-year-old audio cassette, which we all know and love. Here is the 8mm size again, which you see is just about the same width and length as the audio cassette. And down here, as well as in one of my pockets, is an actual DAT standard cassette. This is it. This is what it's going to look like. This is a real one. It's not a dummy. There's tape inside. 2 hours at 16-bit, true 16-bit digital recording. The tape will move at only 1/4 of an inch per second in here. The spinning head, however, will revolve at 2000 RPM. And there's only 150 feet of tape, therefore, in this little cassette for 2 hours of recording. The density is just incredible. Now, interestingly, that relationship, 1/4 inch per second and 150 feet of tape, is also going to make for much quicker access time when you want to locate a particular selection, because the fast forward and the reverse speeds in here are going to be 300 times the normal playing speed or record speed. So if you figure it out, you'll be able to get from anywhere to anywhere in a tape, and there'll be coded information that can be read that fast in 25 seconds over the 2 hours of recording. Now, truly, that's not as fast as you can access on a CD, but it's a lot faster than you could access similarly either on a video tape or on an audio cassette, for that matter. So there it is, and you might want to pass that around and take a close look at it. The wear on the tape is going to be considerably less because in this new format, the head wrap is only 90 degrees. And that in itself will produce less head wear and less tension of tape against the head. So that's been thought of, too, and worked out very carefully. As for the track layout, it looks something like this, very analogous to video recording, for those of you who are familiar with how that works, as I illustrated before. The tape motion is in this direction, and the spinning head on an angle, of course, is laying down these individual tracks side by side, very much like in video. But the standards are different, and they're designed to work best for audio. I do want to do some comparing of 3 audio recording formats that I think will help clarify some confusion that's out there today. At the left, you see the specifications, or a few of the specs, for hi-fi video sound recording. That is, on a VCR that has either VHS hi-fi or beta hi-fi. Both of those systems use a technique called AFM, or audio frequency modulation. You should know that there's nothing digital about that. It is a totally analog system. What it is a couple of FM carriers mixed in with the video, as it were, and able to be FM modulated for good frequency response, 20 to 20, no question about it. Excellent dynamic range, fairly low wow and flutter, not as low as digital, and even the distortion is pretty good, though again, nowhere near as low as digital. And they are fine analog recording systems, but subject to all the vagaries of analog and all the problems associated with analog on tape. Now, here is the confusion that arises. The new 8mm video format was developed quite independently of DATs, different committees working on it. And as you may or may not know, in 8mm video, there's only one mandatory audio recording method that you must use, that a manufacturer must use to be a licensee of the 8mm format, and that, believe it or not, is mono. It's not even stereo. In 8mm, the mandatory audio recording system is AFM again. It's this high-quality analog recording method, but it's mono, one track only. Now, However, in the format, the manufacturer is given options. If they want to, they can incorporate a different audio recording technique as well as the AFM, in addition to. And the one that some manufacturers are choosing to use is a so-called digital PCM stereo audio recording facility. But look at this. It's an 8-bit system. You remember what I said up front about 8 bits? Theoretically, all you should be able to get out of that is 48 dB of dynamic range. But in fact, look, they're claiming 88 dB. The asterisk tells you the reason. They're using stiff, sharp analog companding. That is to say, they compress the signal during recording and expand it out again during playback. It's an electronic processing system similar to DBX or any of the other companding systems you may be familiar with. Now, I'm not against that. That's fine, and it works very well within its limitations. But as some of you know, any such system can always be tricked by certain kinds of music, and you will get some pumping and breathing. Furthermore, look at the frequency response. Only goes up to 15 kilohertz. Now, for video, that's not bad at all, because in fact, TV broadcasting only goes out to 15 kilohertz on its audio as well, whether it be stereo or mono. FM is only out to 15 kilohertz. But you know why it's only 15 kilohertz? You can probably guess from what I said earlier. In the digital domain, the highest frequency is determined by the sampling rate. And the sampling rate here is much lower than on a CD. It's only 31.5 kilohertz. So that allows you to get up to about 15 kilohertz. Remember, we said the most you could get is half the sampling frequency. So my point is, this is a fine system to go along with video. As an audio for video thing, it's not bad at all. But don't confuse it, and don't think that it's as good just because it uses PCM or, quote, digital, that it's anywhere near the fidelity that we're going to be able to get with this new RDAT, which, as you see, uses a full 16-bit true linear digital system, and the frequency response is actually a bit higher than on a compact disc. And by now you can guess why. Because they've chosen a different, higher sampling rate, 48 kilohertz. Now, what that will mean is you will not be able to make a digital-to-digital transfer from a CD to a DAT. However, if this DAT format is to succeed at all, it's clear that there will have to be software as well, or pre-recorded tapes on DAT, right? Just as we have thousands of pre-recorded cassettes today with music on them. And in that format, the standard does call for 44.1 kilohertz sampling rate. And the reason is obvious. Now a recording company can make a single master tape, and from that master tape produce CDs as well as pre-recorded RDATs. Okay, we're not going back to the subject of compact disc players, even though that is a picture of Sony's top model, the 650. It's up there for another reason. Some of you who have examined the back of that unit may know that in addition to the subcode output we talked about earlier for graphics and such, there's actually a digital code output on the back of that model, a digital audio code I'm talking about now. There seem to be other applications coming for direct digital output. And that brings us to the last subject we're going to handle tonight, which is digital signal processing, or DSP. Now, this is kind of interesting. Up until the advent of digital a few years ago, we all used to say that the limiting factor in high fidelity was the source material. You know, the amplifiers had sufficiently low distortion and good frequency response, and so did the preamps. Speakers left something to be desired, of course, but everything in the electronic domain was better than the source material. After all, LPs had 1.5 to 2% tracking distortion, even with the cartridge properly aligned, a fact which not too many people realized. And tape, of course, was subject to hiss, and you had saturation at the high frequencies. So we used to say that the source material was the limiting factor, and it was the electronics that was pure. But today, we're kind of rethinking that whole attitude, because in fact, the source material in the form of compact disc and future digital audio tape is the purest of the lot, of the whole signal process. And so wouldn't it be nice if we could sort of keep things in the digital domain for as long as possible? In other words, take the digital output of a compact disc player, don't convert it back to analog, and send it to something that we'll call a digital signal preamplifier, which in the digital domain still, handling these pulses and absence of pulses, zeros and ones, would process that information so that the tonal balance could be changed. In other words, tone control action could be done digitally, level adjustment could be done digitally, and the other things that we do with a preamp. And taking it even further, we could even go so far as keep it in the digital domain right through the digital amplifier if we wanted to. And really the only place we have to convert, unfortunately, is back at the transducer, because human beings as yet do not hear zeros and ones. We have to, at some point, get it back to analog. But up until then, we could keep it digital. And interestingly, I think that's the direction in which this industry is going to move in the years ahead. More and more digital domain processing of signals. And interestingly, the first unit of that kind is this little device up here, which is just that, a digital signal processor. Now, it's not a preamp, although in many ways it acts like one. What it is a surround sound processor, but it's done digitally. Now, you may be familiar with other surround processors which do time delay or ambience recovery in a room and sort of enlarging the apparent size of the listening space, and even those that do Dolby surround for your video movies that have been recorded using Dolby stereo or Dolby surround, giving you a theater effect with sounds coming from everywhere and so on. Well, that's exactly what this unit does, but it does it in the digital domain. In other words, the two channels going in are analog, and they're immediately converted to 16-bit digital code. And it's in that domain that both the time delay is done, as well as any decoding that's necessary, as, for example, the Dolby decoding. This is a well-known this is the action of a well-known surround sound processor that operates in an analog fashion. There are many of them around, but this is one in particular that we measured. And we applied to the input a unit pulse, a very quick transient pulse. And of course, we got the correct time delay, but this is what came out for the rear channels. Hardly a replica of what we started out with. Compare that, if you will, with the same experiment performed on this very unit. Again, we fed in a unit pulse, and we got out an exact replica with the proper time delay. You can imagine what a difference that will make in what comes out of the rear speakers.
I'd like to say thank you to Harvey's Electronics for allowing this seminar to take place. And I think all of us owe a real nice round of applause to Len for a really good presentation.
Thanks very much. Thanks for coming, and I hope it was worthwhile for you.